Now, something else that we care about in a distribution is known as a quantile. And quantiles are related to the cumulative distribution function. So let's consider a random variable that's a continuous random variable that has a continuous cumulative distribution function. So we have capital F of x is the probability that big X is less or equal to little x. All right? So the definition of the quantile of a distribution, so we take some probability level alpha, and so an alpha is some number between 0 and 1. So the alpha times 100% quantile of the distribution is the value Q of alpha such that the CDF evaluated at the quantile is equal to alpha. Now, the best way of thinking about this is to draw a picture. So the idea here, if this is the probability curve, say f of x, and let's specify some probability here, alpha. Say alpha is equal to 5%. Then the 5% quantile is the value of x such that the probability to the left of the quantile is equal to this probability value. Okay? So quantiles are values in the sample space such that the probability to the left of the quantile is equal to your specified alpha. Okay? So that's, again, the definition of a quantile we think of look at through here. Now, with the continuous random variable, so go back and let's think of fx of x for a continuous random variable. The cumulative distribution function looks like this, and so x is over here. So here's minus infinity, here's infinity over here. And if we have some value x, then the CDF here, and if we is this height. So if this is we put an x scale on this. This is 0. This is 1. Then this is fx of little x. That's the probability that big X is less than or equal to little x. So when we have a continuous distribution, the area under the probability curve, we can write the cumulative distribution function. It looks like this S-shaped function. And so for any value of x, we can figure out by going to the distribution function what this probability is. Now when we think of quantiles, we can think of some probability value like 0.05, and then we can say, given the distribution function, given my probability value, what value of x gives me this probability? So that, again, that defines what the quantile is. So when we're working with a CDF, we take x, and then we get a probability value. And when we work with quantiles, we go in the other direction. We take a probability value, and then we figure out what the quantile is. So in this way, we go to f of x. And then this way, so we end up, we do what's called, we use the inverse function. So when we start from here and then go down, then we're inverting this CDF function given a probability to get a quantile. So the picture that I just described, so if we have a continuous cumulative distribution function, then the inverse of the distribution function exists. And then we can solve for the quantile by applying the inverse function to the random variable. Now the inverse function satisfies fx inverse of fx of q is equal to q alpha. This is equal to q alpha. So when we apply the inverse function to the CDF at a point, then that negates it. So think of like the exponential and the logarithmic function. the exponential is the inverse of the logarithmic function, and vice versa. So e to the logarithm of x is equal to x. So the same thing is going on here. We think of this is the CDF, and the inverse CDF is the function such that it satisfies this property. So if we can mathematically compute the inverse function, then we can get the quantile. So that's why this inverse CDF is often referred to as the quantile function for a distribution. Now, particular quantiles that we're interested in, so the 1% quantile is Q01, the 5% quantile, and the 50% quantile is known as the median. So if we think of a distribution, we plot its probability curve, and if this area is 1%, this is the 1% quantile. The area is 5%. This is the 5% quantile. And then the median is the 50% quantile. That's such that the area is to the left of that. Now we're going to find in finance that quantiles are particularly interesting things because they tell us about the probability of loss. So if we think of the random variable associated with this probability curve as a rate of return, so then and values over here would be negative rates of return, and values over here would be positive rates of return. So this lower quantile represents a small negative number that happens with a particular probability. So when we talk about with 1% probability, how much could we lose? Well, it's equal to the 1% quantile of the return distribution. And we can say with 5% probability, how much could we lose? Then we're concerned with the 5% quantile of the distribution. So these quantiles, particularly when we have distributions that represent rates of return, tell us about the probabilities associated with losing money. And so those are, that's a very important and very interesting way of thinking about risk. Now, sometimes we can figure out the quantile function for a particular random variable. So for example, if we have the uniform distribution, we know that the CDF looks like this. So the inverse distribution function is exactly the same. So for a uniform random variable, if I tell you the probability, I get x. Or if I take x, I get the same probability value. So the inverse function, quantile function, satisfies this property.